Good afternoon, everyone. Thanks for joining in for this discussion on firmware first error handling on Arm Neoverse Reference design platforms. So over the course of next 20 minutes, we'll be talking about RAS as a concept. What are different terminologies that define RAS? What is firmware first error handling? What are different software entities that help enable firmware first error handling? So I'm Omkar. I work at Arm in open source software division, where we enable software reference software stack for ARM platforms. For last 1 year or so, I've been involved in RAS feature development. The agenda for today's discussion would be: we'll start off with what is RAS, what are its advantages, what are different approaches for enabling RAS. The focus of today's discussion is firmware first error handling, where we will talk about different terminologies that are involved in firmware first error handling, and dive into details of each of those. What are different ACPI tables that help enable firmware first error handling? RAS, or reliability, availability, and serviceability, conceptually defines continuity and readiness of the system and its ability to undergo repairs. So system uptime can be used as a measure to define RAS, wherein higher the uptime, more reliable the system is. A system can be called as RAS enabled if it is able to detect and correct all possible platform errors. Platform error handling as such can be um, achieved using two ways: firmware first error handling and kernel first error handling. So there are errors that that are directly delegated to the kernel, wherein the kernel knows how to handle that error. And those classes of errors are handled using kernel first error handling. But there are certain errors which require some sort of pre-processing even before they are getting delivered to the kernel. Such errors are handled using firmware first error handling. So this presentation will be concentrating on firmware first error handling. These are some of the general terminologies that we will be using over the course of this discussion. So error node is an error detecting component within an hardware. It can implement features like ECC or parity along with other features. So an error record is an integral part of an error node, which is defined by a bunch of registers like status, misc, control, and feature. And these registers uh, help to collect the error information when an error node detects an error. So an error node, a single error node can act as an error source. Error is actually a deviation from a corrected service, and fault is cause of that deviation. So in an arithmetic operation, for example, 2 plus 2 equals 4. If the result of that operation is 5, which is a deviation, it is called an error, and uh, the cause of that error is because of a fault, and that fault can be anything. For example, an environmental fault. When an error node detects an error, it can cause an abort or an interrupt. These aborts and interrupts are will be referred to as fault events in this discussion. Common platform error record, or CPER. It defines a standard CPER defines a standard way of representing an error. So the CPER is defined as part of UEFI specification, and there are already standard structures defined to represent memory controller errors, processor errors, and interconnect errors. Software delegated exception interface is a mechanism to deliver extraordinary events to the operating system. SDEI helps uh, delivering high priority events to the operating system, uh, which have priorities higher than the interrupts. HEST ACPI table. Error sources are represented in software using an HEST ACPI table. So the HEST ACPI table is composed of an HEST header and multiple error source descriptor structures. So at boot, when operating system or the OSPM should be aware about all the hardware error sources that the platform is supporting, and this can be done using HEST ACPI table. So the hardware error source table, as the name indicates, is a table that represents all the hardware error sources that the platform is supporting. So let's look at these hardwares which have error handling capabilities, and each of them supports multiple error detecting nodes. So each node within these hardwares can be represented as an error source and hence as an error source descriptor to the HEST table. So main point to note on this particular slide is how do we represent the hardware error sources in software, that is using error source descriptor. Error source descriptor structure. So let's look at one of the error source descriptor structure in detail. So here this is a block diagram of an of generic hardware error source descriptor structure, which is used for representing the hardware error sources. So GHES is composed of mainly of two structures: generic address structure and a notification structure. The generic address structure is used to define the SEPA buffer memory where the error source will be recording its error information. So here there is an error status address, which is a pointer to an error status register, and which in turn points to the actual SEPA buffer memory. The second structure which forms part of GHS is the notification structure. The notification structure defines what is the notification type that the error source will be using or the firmware will be using to notify the OSPM about the error. So here SDEI in this GHS we define SDEI as a notification mechanism that we'll be using. The event number is unique per error source descriptor, and it helps OSPM determine which SEPA buffer it has to read when an error occurs during runtime. So now that we have introduced the general terminologies that we'll be using or which help in understanding firmware first error handling, we will look into the firmware first error handling itself. So what is so firmware first error handling can be divided into two phases. One is a boot time phase and the other is a runtime phase. So at boot, the firmware initializes and it enumerates all the hardware error sources that the platform is supporting. Using those error sources, it generates an HEST table and publishes it to the OSPM. OSPM on initialization reads this HEST table, loops over each of the error source descriptor, and gets to know about all the error sources or the hardware error sources. So at runtime, when an hardware that is capable of detecting platform errors detects a fault, the error detected node within that hardware detects the error and populates the error record registers. Following that, the node raises a fault event which the firmware can capture, and which the firmware captures and reads the error record registers. Using the error information which is part of these error record registers, the firmware generates an or creates a CPER error record into the memory, and also notifies OSPM about the error. The OSPM can then go ahead and read the CPER error record and take uh, appropriate actions. So this is a detailed block diagram of the runtime flow of events that occur in during firmware first error handling. So consider this as an hardware that has error handling capabilities, and it supports multiple error detecting nodes, and has um, can support can detect single bit, uh, double bit errors, and can possibly also correct one bit error as well. So when a fault that occurs on this IP, the error detecting nodes register that error information into the error record register, and notify or raise a fault event, which the platform firmware um, captures. The error handling framework that is present as part of this platform firmware reads this fault event, uh, prioritizes it, and calls the appropriate interrupt handler. The interrupt handler here will do any further processing if required, and will delegate this event to the driver that is present as part of this secure partition. This driver here, the job of this driver is to go and read error record register that is populated by this error detecting node and generate a CPER error record. The driver this call then returns back to the interrupt handler. The interrupt handler here, present as part of platform firmware, will notify the OSPM about this error event. OSPM then goes ahead and reads this CPER error record populated, and takes any further actions. So again, the point to be noted here is this CPER buffer memory is marked as both secure and non-secure access, so that the secure partition is able to populate this CPER error record, and the OSPM, which is a non-secure running entity, will be able to read it. So what is the need of dynamic HEST table? As mentioned previously, the error sources count doesn't remain same for each platform. It varies from platform to platform, and there is no way to define a static HEST table which is common for each platform. So this calls for a need to have a framework in the firmware which can generate an HEST table dynamically. So this is an overall design a software design that was proposed to generate an HEST table dynamically. So consider these as these as hardwares which have error handling capabilities, and each of these hardwares have multiple error detecting nodes. So each of these hardwares are represented by corresponding driver in the secure partition. So these drivers, the job of these drivers is, one, to represent these error sources as error source descriptors, and second, when a fault event occurs on this hardware, read the read the error record registers that are populated as part of these error detecting nodes, and generate a CPER buffer. So these two drivers here collectively help collect all the error source descriptors that the platform supports. How do they do that? We'll talk about that in the upcoming slide. There is also one Dixie driver which is used to create a complete HEST table. So this Dixie driver helps build an HEST header. It implements a protocol which allows appending all the error source descriptors to the HEST table, and it also implements a protocol service which can be used to which basically uses ACPI protocol service to install this generated HEST table and publish it to the OSPM. There is one Dixie driver which acts as a trigger point to install the HEST ACPI table and also publish the HEST and also publish the SDEI ACPI table. So this block diagram represents the overall software flow that happens in dynamic generation of HEST table. So this is an HEST error source Dixie driver in the non-secure space, which initializes first, and it makes an MM communicate call across the secure boundary to get all the to the HEST error source standalone MM driver, which is a gateway driver that collects all the error source descriptors. So this HEST error source standalone MM driver loops over all the MM drivers that are capable of publishing error source descriptor structures. It collects all the error source descriptor structures and collates them as a single MM communicate buffer, and then returns that MM communicate buffer to HEST error source Dixie driver. The HEST error source Dixie driver using that array of error source Dixie um, calls HEST the append protocol service implemented by HEST table Dixie, and appends these all error source descriptors to the HEST table. If there is no HEST table that is already created, this HEST table Dixie will help create the HEST header first and then append the error source descriptors. Once this HEST table is created, this platform error handler Dixie driver, which initializes very late in the boot, will call install protocol, which is implemented by HEST table Dixie, and install this HEST ACPI table and publish it to the OSPM. This platform error handler Dixie will also be installing the SDEI ACPI table. Software Delegated Exception Interface, or SDEI. SDEI, as mentioned earlier, is used as a notification mechanism by the firmware to notify about the error events that happen to the OSPM. So here is we define a block diagram that here there is a block diagram that defines SDEI event registration that happens at boot. Platform firmware at boot time publishes HEST ACPI table, which will be then used by the OSPM. The GHES driver, which is part of this OSPM, will parse over each of these error source descriptors and retrieve the SDEI event number. This GHES driver will then use this event number and along with corresponding notification callback and register it with the SDEI driver. So at runtime, when an fault occurs on the hardware, the firmware reads the error record register, generates the CPER error record, and notifies OSPM about this error. So the firmware will be using this unique SDEI event number, which is already registered at boot time for that particular error. The OSPM will then loop the SDEI driver, which is present as part of OSPM, will loop over all the registered SDEI event numbers and uh, determine which callback it has to call. The callback function will then be invoked in the OSPM and will do any further processing. For example, like reading of zipper buffer. So the current work that is done, which is around the dynamic generation of HEST ACPI table, and the V3 set of patches are already posted to the EDK2 mailing list. With these, there is a reference implementation that is already which is already submitted as part of these patches. This is a reference driver implementation that handles 1-bit corrected errors on BMC 620. There is an active development that is going around handling platform errors on CPU, and it will be followed up with other modules like GIC and SMMU, which also exhibit error handling capabilities. There is an EL3 runtime firmware work to handle platform errors for these also for these hardware modules is also in the pipeline. So to summarize, we talked about firmware first error handling, various components, terminologies, and both in hardware and software that are involved in achieving firmware first error handling. Different ACPI tables that help or that aid in doing firmware first error handling, and also some of the work done that has been done around dynamic generation of HEST table. These are some of the references to the specifications. Thank you, and I'm open to questions.